Welcome to Wave Solutions in 3D, plane waves. So we're going to give the intuitions here around plane waves, and then later on we'll do the algebra once we have the form of the solutions. So how do we do this? Let's start with 1D. We know that our basic solutions are f of t plus or minus z over v, minus sign, waves going to the right, increasing z, plus sign in the other direction. We also saw earlier that you could scale everything by putting a constant alpha in here. And we use that a lot. We use that a lot in our transmission lines. Sam, can you give an example of one of these?
Yeah, of course. I'm sure they will recognize it immediately.
Maybe you want plus?
Oh, okay, right. Looks familiar to you?
Yeah, can you write it in another way by expanding out?
Or
that's okay, you just leave it like that.
yeah?
So fact,
Actually, let's
e to the j omega t times that, and then we'll write it out. So keep going there.
Actually, we can write it in a form more familiar to the students,
Okay,
because they're more used to seeing beta z, right?
Yeah, beta z.
Whoops.
Beta z's good.
We all like beta z.
And then we can expand it. Yeah, beta.
Then the omega would not be factored out.
Yeah, let's start with omega not factored out. So alpha t is going to look like omega t plus or minus beta z. Well, now let's try to get the omega out, so do the factoring.
Sure. Well, we start up here. We factor out omega. T plus or minus beta z, but beta is to divide with
Okay,
omega
now
because we factored it out.
so beta of omega, can we write that a little differently?
Yeah, let's play around with that a little. E j omega t plus or minus. Let's inverse it.
Okay.
1 over omega over beta z. Huh, this looks familiar.
Yeah, what's omega over beta?
Isn't that just v?
That's v, right. So
E j omega t plus or minus z over v.
and that's what we
this
have.
Looks like that?
Yeah, this is exactly that. So that's great. So we know that. So we know how to do it in 1D. What are we going to do in 2 and in 3D? If we could do 3D, we do 2D, so we might as well do 3D. So let's have a guess. Sam, how about a guess?
Sure, let's go with a very straightforward guess. If we started off like that,
yeah.
What about we just add more terms? Add a x term, add a y term.
Add an x term, add a y term. So
what would happen?
We'll look at this form here.
Sure.
So t plus or minus x over v plus y over v plus z over v. Well, what do you think? I think we got to do something else here. We know what this is here, and we know what it is here. Let's look at this form.
Okay.
And beta z here, now this is in 1D.
Yep.
So two scalars, beta multiplied by z.
Yep.
But we're now in 3D. So let's kind of combine this idea with this and see if we can come up with the exact form of all three coordinates.
It sounds good to me.
So we want to write beta z. So this is our guess. Continuing on with our guess, we want to write beta z in 3D rather than 1D. Now beta z is a scalar, so how do we do that?
This is some scalar, but if you want to get a scalar out of 3 dimensions, then you have some sort of dot product.
Dot product, right. So let's do the dot product here. we're going to write beta z as a dot product in
Sounds
3D.
great to me.
So you go ahead.
Oh, sure. Well, it's only the z direction, so we have 0, 0, beta, dot, 0, 0, z. So when you take the dot product, you only get beta z.
Yeah, that's right. And we'll use this and see if we get something like that. So
Okay.
let's generalize this to three dimensions. So 3D, we're just going to replace this and fill up the zeros.
Sure.
So we'll say, we'll have, instead of this, we'll replace what we did with the zeros here, zeros, like this. So we'll have, I don't know, let's call it M,
And, oh, sure.
M beta, dotted with, oh, this part is easy,
Yeah, x, y, z.
X, Y, Z. And notice that if we're at a fixed point on the wave here, Z is a constant. So if we're at a fixed point on the wave here, this is fixed. So we're going to have that equal to a constant.
Okay.
And now we have to interpret what all this means. So beta z as a constant means we're sitting at a particular point on the wave and seeing how it wiggles in time.
And a 1D.
In 1D. Now we're going to be in 3D. So what exactly is this geometrical picture? Because this just represents a point. So a point in 2D becomes a line, and in 3D
Then it becomes a plane.
plane. So let's check it out. Let's see if we can write this as a plane. So how we do that is we draw a picture. We're going to do the 2D picture.
Much easier to draw.
Yeah, so here we go. So 2D picture, and here it is. We'll put in our axes, X and Z. And now we'll draw our plane, which in 2D is a line. And the line has a normal vector. Normal to the line. You can think of this as a 3D picture. If we pull this line out of the page, it's a plane. So we're just slicing the plane. Since it's not tilted in Y, things don't change. So just a line. And we want to look, we've got the normal, and the normal will have some components. And when we're talking about waves, we usually call it, this is going to be kx, 0. So kx is like m. We're not worrying about varying y. And there's my normal. And now we want to look at a particular set of points on this line. And we can describe
to
that.
define where the line could be, right?
Where the line could be. So a perpendicular vector to the line, that point there is, we'll call R0.
Okay.
And a generic point would be over here somewhere. And this is R. So if we subtract R minus R0, where are we? Where does that put us?
Well, then,
yeah, go ahead. So where is it? It's here.
yeah.
All right, so R minus R0 is this vector here. So let's draw it. There's R minus R0. That's this vector. Now, this vector, how's the R minus R0 related to the vector K? What's the angle between them?
Oh, then they're just normal to each other.
They're just normal to each other. So what's the condition of normality? Oh, you got one already.
Oh.
Yeah.
So I guess when you dot them together, you get 0.
Okay, let's do it.
So this dot that,
Yep.
R that minus R naught dot kx 0 kz.
Right.
Which is just a k vector.
That's just R minus.
Is 0.
Right. So this is K. So if we finish the algebra, we get R dot K minus R0 dot K is equal to 0.
But we already know where R naught is, so we can actually evaluate this dot product and get a value out of it.
This is a value that's fixed on that line, because R0 is fixed from the origin to the line. And so we got R dot K is equal to a constant. Now, R only has X and Y. That's a generic position, X and Z, and K has Kx and Kz. So do you want to write down what that dot product is?
So we have some Rx, Kx, and then Y component we take 0, plus Rz, Kz is the constant.
Yeah, and Rx is just the X component of R, which is just
Oh, okay,
X.
yes.
Kx plus Z, Kz is
Beautiful.
equal to a constant. And there's our answer. So what will it be in 3D if we had a 3D picture?
Just throw in a Y.
Yeah, Y, Ky. So the big difference is we now have waves have a constant value, not at a point, but on a plane. And that plane moves normal to itself and carries the wave energy. So let's see what that means on the next board in terms of the algebra now. Okay, so let's continue on.
Sounds great to me.
Okay, so the first thing we have is we had before beta equals 2 pi over lambda. That was for transmission lines in 1D. And now we have the great new thing is that this is replaced by a vector. Vector.
Some K.
Yeah, some K, and that's going to be Kx, Ky, and Kz. All right, Sam, we need to calculate the magnitude of K. How do we do that?
Don't you just add the square of them and
Okay, let's
do a square root?
Let's add the sums of squares and square root. So K magnitude is equal to square root Kx squared
Looks right to me.
and this must be, oh, what do you think in terms of wavelengths? What do you think this should be? It certainly has to be correct when we have 1D. So what do you think?
You mean we can just replace these by these, but with x, y, z components?
Well, we can replace those by x, y, z, so let's do that. Well, we can't just put in 2 pi over lambda. If we do that, you can see what happens. We'll get something crazy. 2 pi squared plus 2 pi squared plus 2 pi over lambda all squared.
That does look bad.
That doesn't look too good. So let's do something else. Let's just say that we're going to guess, here's another guess, that when we take the magnitude, it's still inversely related to the wavelength. And then in our example, we'll show exactly by counting wave crests what Kx and Ky and Kz should actually be.
Okay.
So let's just put that equal to 2 pi over lambda. Now, how about in terms of omega? So we know what lambda is in terms of omega, right? So lambda in terms of omega. So lambda is equal to the velocity times v equals f lambda. So lambda is v divided by f.
Yep. You put the f up.
2 pi f over v. Now this is a scalar v. Okay, so let's, what's 2 pi f?
Omega.
Your show. Now, if we were to think of v, v is a scalar, but we might think that in some cases v might be a vector, and this v here actually would be the v that we see is actually the magnitude of a vector v. And we know what that would be in terms of sum of components. And we also know that the magnitude of k is equal to
Do you want to use this one?
omega over v. Yeah, that's better.
Yeah.
You want to omega over v, which is equal to, do you remember what v 1 over v is in terms of mu and epsilon?
Huh. 1 over square root of mu epsilon.
And it's in the denominator.
So you put it up.
Put it up. So that's still good. And we'll use all this stuff later on. We'll see what kx and ky and kz are in terms of lambda x. We'll have a lambda x and a lambda y and a lambda z, and it all makes sense. We'll actually go for a visit to the beach to see how this all works out.
I'll go pack up.
Okay, and while you're packing up, I will just close off by saying that we'll use this stuff on plane waves to actually substitute in E and H in this form, and we'll do that as an exercise. So that's a constant vector amplitude, e to the j omega t minus k dot r, and the same for h. And we'll see how, when you substitute that into the Maxwell equations, we can see how that all works. Why have you got a garbage can here?
No, I'm backed up. I'm backed up.
Is it a lot of garbage? You taking this to the beach? Wow. That isn't very good ecology. Okay, well, we'll talk to you later. We got to sort all this out.